small record. Hey.
Okay, so 欢迎大家参加今年的许振荣讲座。
That's good. Congratulations.
如果没有位置的，在隔壁间可以有实况转播，在201有实况转播。There is a simulcast in room 201 if you can't find a seat. So welcome to this year's Chen-Jung lectures. Let me start with a very short introduction about this lecture. So Professor Chen-Jung was born in Taipei, Taiwan, and he got his PhD from Japan, and then he came back to Taiwan in 1946 and joined the faculty of Department of Mathematics in National Taiwan University. In fact, he was from 1963 to 65, the acting director of the Institute of Mathematics, Academia Sinica. And then he moved to US, and then he returned to Taiwan in 1981 as a research fellow in the Institute and retired in 1988. In memory of his great contributions to the mathematical development of Taiwan, so the Taiwanese Mathematical Society and the Institute of Mathematics, Academia Sinica, established Chen-Jung lectures starting 2011. So the goal was to invite the world-class mathematicians to give. The goal was to invite world-class mathematicians to give great lectures to general mathematical audience. And this year, we are very pleased to have Professor Persi Diaconis from Stanford University, and that certainly raised the bar in terms of scholarship and exposition. Professor Diaconis is currently a Mary V. Sunseri Professor of Statistics and Mathematics at Stanford University. Before joining Stanford, he was also a professor at Harvard University. And his CV is so long and he was so prolific, probably it will take an ordinary moral of like myself, many lifetime to accomplish that. And among his many distinctions, he got in 1982 he was awarded the Genius MacArthur Fellowship, and in 1990 he was a plenary speaker at the ICM, and then he's also a member of National Academy of Sciences and American Philosophical Society. So let's welcome Professor Persi Diaconis.
Good early afternoon. I hope everybody can hear me. And this is the first of a series of lectures, and the topic is a little unusual. It's adding numbers. And shuffling cards. And I know that this is a serious group of mathematicians, and you may think, wait a second, we're graduate students, we're professors. This guy is going to talk about adding numbers and shuffling cards? Wait a little while and see how it goes. So what I want to tell you about is some of what we know about adding numbers and shuffling cards, and then I want to try to explain that they're very closely related. And so let's start with adding numbers, and I mean and I guess, do they do it the same way here as we do? You know, 2 and 5 are 7, 3 and 7 are 10, and when there's a carry, you make it a carry, and 8 and 1 plus the 1 is 10 again, that's 15, and there's a 1, and that's 12, and there's a 1. Well, there are a lot of carries here, but so that's 6, 14, and there's a 1, and that's 11, there's a 1, and that's an 8. So when we add numbers in the usual way, carries occur along the way. Yeah, okay. How do you do it here? Do you do it underneath, or do you do it on top the same way? Same way, okay, sorry, but okay. And if you're me, and hopefully you after this talk, it's not unnatural to ask, how do the carries go? I mean, how many carries are typical? If you just had a carry, you're more or less likely to have a carry the next time. How does it depend on the base, B? And what if I add 3 numbers or n numbers? And that's what we're going to talk about for a few minutes. And let's see where to start. So I guess one place to start is to make math of carries, because this is a math talk. And so let me make math of carries this way. So I'm going to write my digits in this funny way. I'm going to write x 1 0, the 0th column, x 1 1, x 1 2, etc., and then x 2 0, x 2 2, x 2 1, x 2 2, etc., some number of digits, and then I'll be talking about adding in numbers, xn 0, xn 1, xn 2, ... Okay, and of course, when you add, and so these digits where 0 less than or equal to xij, my digits less than or equal to b minus 1, I'll be working base b, base 10, base 2, base 8, base b, so you add the first column, you have some S0, S1, and of course, there's never a carry in the first column, so I'll call the carries kappa. Kappa 0 is 0, and then there's kappa 1, kappa 2, etc. So the carries are going to be called kappa. And now I can make a well-specified math problem out of this by saying that I'm going to look at typical numbers. That is, my digits are going to be chosen uniformly at random between 0 and b minus 1. So the way we say it is that xij are independent and uniform on their range. And now that's a math setup and well specified, and so you can ask now. So the carries are now a random process. And there they are. Okay, so I've defined a mathematical object, and now so here's fact one. The carries form a Markov chain. Let me try to explain what that means. So of course, because the numbers are random, the carries are random, and what it means to say that they form a Markov chain is that the probability that the next carry, say the a plus first carry, is equal to j, given that the last carry at time a was equal to I, and the past kappa a minus 1 kappa 0. So if I tell you how the carries went, I tell you the past of the carries, what's the chance that the next carry is anything? It's obvious if you look at it and think about it that it only depends on the last carry. It's equal to the chance that kappa A plus 1 is equal to j, given that kappa A is equal to I. And that's obvious because if I tell you the past of the carries, I just tell you what happened up to time I. What about the next carry? Well, all that the next carry depends on is, of course, what happened at time I and the numbers under I, but they're random and independent of everything else. So whatever happened in the past just doesn't matter. And so the carries, this is the definition of a Markov chain. The future depends on the past only through the present, and so that's a fact about carries. So that means that there's a matrix which I'll write here. So there's a matrix Pij, which is equal to the probability, the chance that the next carry is j, given the one before is I. That is this, and this is an n by n. So this is an n by n matrix, and so I'd like to say that I invented that matrix, but it's not true. So let me tell you the story of that matrix. So I was visiting Nice in south of France, and I was doing some terrible thing like ranking candidates on an exam, or who should we hire, or grading papers, something that I didn't really want to do so much. And I was using somebody else's office, and so I thought, oh, I wonder what this guy worked on. And in front of me, there were some issues of the American Mathematical Monthly, which is a friendly, readable, accessible journal. So I picked up an issue of the monthly, and I looked at the cover, and I saw there was an article called Carries, Combinatorics, and an Amazing Matrix. And that's going to be this amazing matrix. Amazing matrix. Amazing matrix. Matrix. But I'll put question marks there. But that, and my reaction was what maybe yours, amazing matrix. Are any matrices amazing? Somebody's selling a little too hard. So, but this is the carries matrix, and so an article by a man named John Holton. So let's look and see what kinds of things he figured out. So there's a handout for this talk, and the matrix is messy enough that I want you to look at. I can get started. So when n is 2, if I add two numbers the way I was talking about, the matrix is this. It's 1 over 2b, and it's b minus 1, b plus 1, b plus 1, b minus 1, and what does this mean? So these rows are labeled. When you add two numbers, you can either have a carry of 0 or 1. So if you just had a carry of 0, the chance that the next time, if you just had a carry of 0, the chance that the next time you have a carry of 0 is b minus 1 over 2b. And that was what the matrix is. And I wrote it down when n is 3 because I don't want you to be fooled into thinking maybe the matrix is symmetric. It's not a symmetric matrix. If you look at the matrix when n is 3, it's just not symmetric. It's not self-adjoint in any inner product. It's not symmetric, okay? And I want to try to copy it down, but you have it. For general, I think the matrix is called K, sorry, but for general I and J, you can write down what the matrix is. It's not rocket science. It's just if I have a sum of independent uniform random variables plus kappa I, what's the chance that the sum is in between two limits? And if there's one thing we know about in probability is sums of independent uniform random variables. We know anything you want to know about them, and you need to know about them, but that's where this expression comes from. For general N, this is the carries matrix. So it's a horrible looking thing. And, but not always. When you work base 2, it cleans up and the sum, it's this nice matrix. The ijth entry is the binomial coefficient n plus 1, 2j minus I plus 1. So sometimes it's nice. So that's the matrix, and I want to take you through a little bit of what John Holt did. So what's so amazing? So okay, so fact 2. So this matrix is not symmetric or reversible or self-adjoint, but it has all real eigenvalues. So the eigenvalues are, it's a stochastic matrix, one of them is 1, then 1 over b, 1 over b squared, 1 over b to the n minus 1. It has nice eigenvalues. Why that should be, that I don't actually know, but we'll go on. And the eigenvectors are explicit too, and that's not so usually the case, but the eigenvectors are explicit and free of b. They don't depend on b. So the eigenvalues are nice. A second fact about this matrix, fact 3, the stationary distribution, so let me explain that. So the stationary distribution, it's a left eigenvector of this matrix with eigenvalue 1, but I call the stationary distribution pi of I, 0 less than or equal to I less than or equal to n minus 1, and I just write down what I said, pi of I times k ij is equal to pi of j. That's the condition, I equals 0 to n minus 1. That's the condition that it be a left eigenvector. But what it really means is the stationary distribution means if you've been running the Markov chain, if you're adding a long string of digits, what's the chance that you have a carry of I? After a while, it settles down, and pi of I is the chance that you have a carry of I. And so, for example, so the stationary distribution is something you want to know about a Markov chain, about a process. And it's just saying, for example, with 2 numbers, you might guess, even though you wouldn't guess it from that example, maybe half the time you have a carry of 0 and half the time you have a carry of 1. That sort of makes sense, right? It's true also. And, but if you want to think about it intuitively, suppose I add 3 numbers. What is it? How does it? Is it a third, a third, a third? Well, you don't know. Right? Probably you don't know. Okay, well, the stationary distribution is nice also. Pi of I is equal to a n I over n factorial, where a n I is the ith Eulerian number, that is, it's equal to the number of permutations sigma in the symmetric group Sn with I descents. And so I remind you 6, 5, 1, 3, 2, 4, I don't know, 7. There's a permutation of 7, I hope, and it has descents. It went from 6 to 2, it went from 5 to 4, went from 5 to 4. This permutation has 2 descents. So the descents in a permutation are, the up-down pattern and where it descends. And I would write d of sigma is equal to 2 here because there are two descents. And so ANI is the number of permutations which have I descents. So let's do a few examples. When n is 2, for example, well, the symmetric group on 2 letters has 2 permutations, 1, 2, and 2, 1. The number of descents, this one goes up, you know, and so it has 0 descents. This one has 1 descent. And so pi of pi, let's subscript it, pi sub 2 of 0 is equal to 1/2, and pi sub 2 of 1 is equal to 1/2. And so that says that if you add numbers, 2 numbers, you know, half the time in the limit, as you go on, half the time you have a carry of 0, and half the time you have a carry of 1. Let's try n is 3. N is 3, so there are 6 permutations. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. I wish I had $1 for every time I've written those down. And how many descents are there? Well, this one has no descents, it goes up. This one has 1 descent, 1 descent, 1 descent, 1 descent, and 3, 2, 1 has 2 descents. Yeah. And so A3, 0 is 1, A3, 1 is 4, and A3, 2 is 1. And so pi 3 of 0 is equal to 1/6. Pi 3, 0 is equal to 2/3. And pi 3, 1, 2, sorry, 0, 1, I can do this, 2 is equal to 1/6. So that's what happens. If you add 3 numbers, 1/6 of the time you have a carry of 0 or 2, and 2/3 of the time you have a carry of 1. Now, if you're you should be thinking, or at least certainly I was, wait a second, this is talking about adding numbers, right? What's the symmetric group doing there? What is it doing there? I mean, what are permutations doing in this problem? Where did they come from? Okay, so we're gonna come back and talk about that. But we know everything we want to know about the Eulerian numbers, and so we understand this. It looks like the bell-shaped curve, and it's just beautiful, famous distribution that we've been studying for a long, long time. So that was fact 3. Fact 4. Now, don't throw things at me, but this matrix, where is it? That matrix, it has a parameter in it, which I've been calling B, right? Well, I could write this equation down, P sub A times P sub B. This is the product of 2 n by n matrices. Once some working base A, once some working base B, but I could multiply the matrices, okay? Well, fact 4 is that this is P sub A times B. And I'll give you $10 if you can prove it from that formula on that. I never knew anybody who could, well, maybe some people. But no, if you have to like messy sums, it wasn't so easy. Now, when I saw these facts, Jason Fullman was visiting Nice also. He's my student, and I ran downstairs with the paper in hand, and I said, Jason, this paper is all about card shuffling. Now, to you may think, wait a second, for this guy, everything's about card shuffling. Well, let me try to convince you that these facts, and indeed all the math of carries that I'm going to be talking about, and then various conclusions, are actually very, very closely related to shuffling cards. And so, wait a second. New talk starting, okay? You're bored, what is this talking carries? New talk is starting. So, Persi Diaconis, hi, very nice to be here. And no, in order to explain, of course, I have to tell you a little bit about the mathematics of shuffling cards. And so let's talk about that a little bit. But it is a completely new talk starting. Okay, So this talk starts with a question. I guess I could write the question here. How many times must a deck of cards be shuffled to mix it up? Okay, that's, you know what I mean by that as a question in English, but we have to make math out of that. And so in order to make math out of that, I have to define shuffle and I have to define mix. And let's start by doing that. So the most common way of shuffling cards, at least in Western society in the last 150 years, is riffle shuffle. So, you know, you cut the cards about in half, you go, shuffle them together. Do that, okay? So let's make math out of. Okay, so what do? I cut off about half the cards. So I cut off C cards. 0 less than or equal to C less than or equal to N with probability N choose C over 2 to the N. This is the discrete version of the binomial distribution. It's the discrete version of the bell-shaped curve. It looks like that. So of course you don't cut them perfectly in half. You cut about in half. You know, and that's what this does. So the card's about in half. So I cut off C cards, and then I start dropping them with my thumbs. So if at any stage, if you have A cards in your left and B cards in your right, so this is the left, this is the right, this is A cards here, this is B cards here, and I'm dropping them with my thumbs one at a time. The chance that the next is from the left is proportional to packet size, is A over A plus B. So let me try to let you look at that for a second. So maybe I cut the cards exactly in half, 52 card deck. And so, okay, you know, the chance that I drop the first card from my left hand is a half. And now there are 25 cards here and 26 here. So the chance I drop the next card from the left is 25 over 51. And so forth. So you're more likely to drop cards from the bigger packet, and that is a pretty good model for the way real people shuffle cards. It's not a good model for the way I shuffle cards. I shuffle cards almost perfectly, 1, 1, 1, 1, 1, and now that sounds good, but you know, if you shuffle cards 8 times perfectly, they come back to the order they started in. It's not such a good way of mixing things up. It's a good way of manipulating cards and doing card tricks and things of that sort. But this is a good model for the way real people shuffle cards. And the reason I know that is I asked people to shuffle cards, and I got the data, and I compared it with this model. And it's quite a good model for the way real people shuffle actually. So this completely specifies a mathematical model for shuffling, right? You just keep going, dropping left, left, right, right, right. You know, this model. So let P of sigma be the chance of sigma after one shuffle. And we'll write it down with formulas, but this, you know, you could write a computer program. You could, I couldn't, but you could write a computer program to do this after one shuffle. Okay, so that's one shuffle, and now we keep shuffling. So P star P of sigma, what's the chance of the deck being in the arrangement sigma after 2 shuffles, is equal to just P of eta, P of sigma, eta inverse, here sum over eta. So the chance of the deck being in the arrangement sigma, you have to do something your first shuffle, and then pick the permutation that takes you to eta, that takes you to sigma, your second shuffle. So it's convolution on the permutation group. And and then you just keep going. So you therefore have defined P star K of sigma. The chance of being at sigma after K shuffles, it's well defined anyway from this model. Now there's also U of sigma, the uniform distribution. Is 1 over n factorial, the uniform distribution. And the first theorem in the subject, due to Poincaré around 1890, it's a little theorem, but it is a theorem that P star K of sigma converges to U of sigma. And as K goes to infinity. And that just says if you shuffle cards a lot, they get all mixed up. And you knew that before you came in here. But we want to be more quantitative about it. And so we're going to define the distance of shuffling after K to the uniform distribution. This is a definition, the total variation distance. It's the maximum over A contained in Sn of P star K of A minus U of A. So let's look at this for a second. So A is a subset of permutations, like all permutations where the ace of spades is in the top half. And P star K of A is what's the chance that the deck is in an arrangement in A after K shuffles. U of A is if the deck is perfectly shuffled, well shuffled, what's the chance of A? And you take the difference between those two numbers and you take the worst case. So if that's small, it means for any question you want to answer, for any game, you've shuffled enough. You're close to random. And how small it is, you have to tell me. But well, I'll explain. So with all of this specified, that is I've defined shuffle and I've defined mix. I want this to be close to 0. We now have a well-specified math question. Given epsilon greater than 0, how large K so that the distance is less than epsilon. That's a math problem. And okay, now I'm going to ask a question that I don't hear asked in rooms of this sort often enough. So I'm going to ask a question. Okay. Just for an aside for a second. Question. We never ask that question, math, right? Somebody else cares, right? But, you know, people know if you shuffle a deck of cards 3, 4, 5 times, it's all mixed up. Well, like so many things that people know, it's just wrong. That's all. And there are wonderful answers to this question. One comes from magic tricks, one comes from card games like blackjack and bridge, and mathematical answers to it too. But I want to give you an answer that will give you something to try when you go home. There was a lady here who I took a picture with. She was wearing a gold dress. She's gone. She came and she left. Oh, oh, it's you. What's your name? Be brave. Carol. Okay. So I'm going back home. Suppose I'm back at Stanford. Carol's still here, but I write her a letter. Dear Carol, nice to meet you. And I thought you might like to see a card trick. And notice that I've enclosed a deck of cards with this letter. And this deck of cards. And would you take the cards out of the case? Okay. Give them a cut. Give them a shuffle. Give them another cut. Give them another shuffle. Cut them a few more times. I'm sure you'll agree no living human could know the name of the top card. You know, you're here, I'm there. Okay. Take that card off, look at it and remember it. Say it's the 6 of hearts between us, and then put it back in the middle of the deck. Give the deck another cut, give it another shuffle, mail me back the deck. Oh yes, and at 6 o'clock every evening, concentrate on your card. It's important. And then in a week or two, or however long the mails take, she gets a note back saying it was the 6 of hearts. So I want to explain how that trick works, and you can try it, and it's a pretty good trick. And that'll give you some insight into the physics of shuffling cards. So, of course, the deck I send Carol is arranged, and probably what I do is just shuffle it up and then write down the order of the cards. But for our description, let's suppose it's 1, 2, 3, up to N, okay? Okay. And now, when you shuffle a deck of cards once, why isn't it random? Well, you cut them someplace, and you shuffle them. The cards that you cut, the top half, are still in increasing order. And the bottom half is in increasing order, right? So the deck after one shuffle has 2 rising sequences, right? Now I wish I could do this, but I can't. Now I suppose I shuffle them again. So I cut off about half the cards. That top half has 2 rising sequences. The bottom half has 2. When I shuffle them, I'll have 4 rising sequences. After 3 shuffles, you have 8 rising sequences. When she takes that card off and puts it back in, it breaks one of the rising sequences. Okay, so makes a 9th rising sequence of length. What do I do when I get the deck in the mail? I just start playing solitaire. I turn up the top card, say it's the 4 of spades. If the next card was the 5 of spades, I would play it on the 4. Suppose it's the 7 of diamonds. Well, I start another pile. Next card, Queen of hearts. Ah, there's the 5 of spades. I put it on the 4. And then you just keep going. Anytime you turn up a card where the one before it in the order cyclically, because she's cutting, is already visible, you play it on. If you try that, you'll find you have 8 piles, each about 1/8 of the deck, and a 9th pile of size 1. Okay, so I'm not lying. You can go home and try it, or you could think about it. It's not a bad trick, and if you want to actually perform it, come and talk to me afterward. And no, I'm not leaving anything out, but there's more to say. And so if that is true, and it is true, 3 shuffles are not enough to mix up 52 cards. Yeah, and I want to call to your attention that I don't care how she shuffles. She doesn't have to follow this model. If you riffle shuffle, because, cut off 4 and, make clumpy, awful shuffles, make perfect shuffles. If you riffle shuffle cards 3 times, you can have at most 8 rising sequences in the deck. Okay. So by similar reasoning, you can see, well, after 5 shuffles, you can have at most 32 rising sequences, and then by counting, we know how many rising sequences there should be. You see that omits a positive proportion of the permutation. So 5 shuffles, no matter how you shuffle, not enough to mix up 52 cards. So that's an example of who cares. People do play cards, and I do consulting for casinos, but actually when I go to, when I meet card players, they say, "Oh, you're the guy, 7 shuffles. I hate that." Okay, so now what does a theorem in the subject look like? I'll write it down 2 ways. Well, let's write it here. Theorem. So first I'm going to tell it to you for numbers when n is 52. And so, here's k, the number of shuffles, and here's the distance of p star k to uniform. And 1, 2, 3, 4, 5, 6, 7. Okay, and now this distance that I'm using is the difference between 2 numbers which are between 0 and 1. So it's between 0 and 1, and it's 0 if and only if the 2 measures are the same. This measure is equal to that measure, and it's 1 if they're if they're completely different. And so you start, the deck is all in order, and it's nothing like random. And so the distance is, well, to 3 decimal places 1. Look, no notes. Okay, the distance is very, very close to 1. Now, actually, you know, this is 0.9999999, maybe 11 nines, but didn't think you'd want to know that exactly. At 5, something happens. It becomes 0.92, 0.92, and then at 6, it becomes 6.64, and then at 7, it becomes 0.32, and then at 8, it is 0.16, and it goes down by a factor of 2 every time you shuffle another time, and that's a theorem, forever. So how many times do you have to shuffle a deck of cards? Well, you have to tell me what epsilon is. But if you tell me what epsilon is, I know how far to go from this math. Okay, so this is a project I did with Dave Beyer, who's a computational algebraic geometer, and we actually know these numbers to 70 places of rational arithmetic, but I didn't think that was relevant for this talk. So that's what it looks like with numbers. And I'll draw a picture of this in a second so you can see it better and try to explain it. As a math theorem, and I'll write David's name down just so I feel better about it. Let k equal 3/2 log to the base 2 of n plus c. Let's write it down. Then the distance of p star k to uniform is equal to 1 minus twice capital phi of minus 2 to the minus c over 4 times the square root of 3 plus big O 1 over root n. So let me parse this for you a little bit. And where capital phi of x is the area under the normal curve, minus infinity to x, 1 over the square root of 2 pi e to the minus t squared over 2 dt. So let me help you look at this. So k is the number of times you shuffle. Well, you know how many times you're thinking about shuffling. You know n, the deck size, and so that determines c as a function of k and n. Right? So c is really ckn. And it could be negative, it could be positive. It's just the difference between 3/2 log to the base 2 of n and the number of times you're thinking about shuffling. Here's our distance to randomness, and this thing, so you have to be friends with the normal curve in order, it's hard to look at. So let me draw a picture of it. Here's the distance, p star k minus u. Here's k, and what this looks like is this, and it breaks at 3/2 log to the base 2 of n. So the normal curve, you know, when c is a little bit large, this thing is 0, and the normal curve at 0 is 1/2, and the area under the normal curve at 0 is 1/2, and times 2 is 1. So this tends to 0 exponentially fast. You can actually see the factors of the powers of 2 coming in from this formula, and you can see them in numbers. And it actually tends to 1 if you shuffle a little less than 3/2 log to the base 2 of n. It tends to 1 doubly exponentially fast. So there's a very sharp transition from order to chaos in this shuffling story, so that's a little bit about shuffling, and I'll want to say a little tiny bit more. Remember, there were 2 talks, right? There was the first talk about adding numbers, right? And then there's this talk which we just gave, right? About shuffling. So I claim they're connected, right? So it's not so obvious, right? Okay, in order to explain the connection, I need to tell you the tiny little more about shuffling, so I'll call it the connection. And I'm going to describe shuffling. I described it there by physical model in a different way. To shuffle is x. The results of the map x goes into twice x mod 1. This is called the Baker's transformation. And let me explain that. So here's the unit interval. Here's 0 and here's 1. Drop endpoints down at random. Okay. Just IID uniform, if that means anything to you. Just drop points down at random and then label them left to right. X1, X2, X3, Xn. Okay, so now what does the Baker's map do? It takes the left half of the interval and it stretches it out, doubles it. X goes to twice X mod 1. It takes the right half of the interval, stretches it out, and the points shuffle together. It's not a very hard thing to do to see that the measure induced on permutations by the Baker's transformation is exactly the Gilbert-Shannon-Reed's measure. It's not so hard to see that. So that's just another way of talking about shuffling. But once you've written that down, it's not at all unnatural to think about A shuffles. A shuffles. That is, X goes into AX mod 1, where A is an integer. Otherwise, there's trouble. So what's a 3 shuffle? So what's a 3 shuffle? Well, two ways of saying it. You drop points in at random. You take the left third, you stretch it out. You take the middle third, stretch it out. Take the right third, stretch it out, and they shuffle together. With cards, it's this. You cut the deck of cards into 3 piles according to a trinomial distribution, and then you start dropping the cards where the probability of dropping a card from a pile with A cards is A over A plus B plus C, with probability proportional to packet size. That's a 3 shuffle, and those are the same models. So A shuffles is not a natural thing to think about, and once you've thought about it, it's obvious that P sub A, if I do an A shuffle and I do a B shuffle, that's the same as doing an AB shuffle. Because, you know, X goes into AX mod 1, goes into BX mod 1, that's the same as X goes into A times B mod 1. So you have to think about that for a second. But so this is great because it means I want to study, so we've been talking about 2 shuffles, P2, this fact says that that's P2 to the K. So I only have to know about A shuffles, and I know about everything about shuffles, right? Because of this convolution fact. Now, so that was what triggered it, but also the eigenvalues of shuffling, it's a Markov chain on permutation group, are of B shuffling, the eigenvalues of B shuffling are 1 over B, 1 over B squared, 1 over B to the n minus 1. They have different multiplicities. We know what the multiplicities are, but the eigenvalues are the same as the eigenvalues of carries. And but in the proofs of the shuffling theorems, there are descents and Eulerian numbers all over the place. And well, let me just say this. What we showed, in fact, was the PA of sigma, the chance of sigma, the main real theorem we proved, the PA of sigma was equal to n plus A minus R, choose n, over A to the n. Now that's a little funny looking because the left-hand side depends on sigma and the right-hand side doesn't seem to, but here R, which does depend on sigma, is equal to the number of rising sequences. So let me explain that. So if you have a permutation where you find 1, and if 2 is under, then 3, so you can take out a first rising sequence, just remove it. And then there's, 7, 8, 9, 10, remove that. You can decompose a permutation uniquely into a disjoint union of rising sequences. And R is the number of rising sequences in a permutation, but also R of sigma is equal to 1 plus, is equal to the number of descents in sigma inverse. Let's see, the number of rising sequences is at least 1, and so it's minus. You see, the number of descents can be 0, so plus 1, right? So the number of rising sequences is the number of descents in the and so this distance I was working with. So there are Eulerian numbers all over the place. Let me say this. So this distance I was working with, p star k minus u, well, it's equal to the sum from I equals 1 up to how many rising sequences you could have n of this formula, 2 to the k plus n minus I, choose n, over 2 to the nk, that's the chance, minus 1 over n factorial times a ni. So because we know the chance of being at a permutation only depends on the number of rising sequences, you get down to this sum, and of course this sum you could just calculate exactly, but if you like the kinds of calculus that I like, well, Stirling's formula and some other things, you can do nice asymptotics, and that's where this theorem comes from. So there are Eulerian numbers all over the place. So it had to be that these two subjects are the same. You know, it just had to be. So now you're where I was. That is, I'm sure that adding numbers is the same subject as shuffling cards. It has to be. I mean, because it can't be that these things, that happens to us all the time in mathematics. You know, this must be related to that. That's what research is about, right? So let me tell you about the connection. I'll tell you especially if I can erase the board. And I know that someplace there's hidden an eraser. And well, I have, be prepared. No, or is it, you know where there's an eraser? Okay. So what's the connection between the two subjects? And I'm just going to tell it to you, but of course I'll explain. Thank you, Jesse. So what's the connection? And I'm going to state it as a theorem, and then I'll try to unpack it. So here's a theorem, and it goes as follows. Let kappa naught, which is 0, kappa 1, kappa 2, be the number of carries, when n numbers are added mod b. You know, with base b. So that's the first part of the talk. And let d0, which is 0, d1, d2, etc., be the number of descents when in cards are repeatedly be shuffled. So let me turn around and explain that. You know, the deck starts out in order, 1 up to n, so it has no descents. It's a D0, the number of shuffles after the number of descents. But then you shuffle it once, it has some number of descents. That's called D1. You shuffle it again, it's got some other number of descents. That's D2. So it's just the number of descents after repeatedly shuffling, okay? And the theorem says that then the probability that, kappa 1 is equal to epsilon 1, kappa 2 is equal to epsilon 2, kappa m and you go and stop anytime, is equal to epsilon m, is equal to the probability that d1 is equal to epsilon 1, d2 is equal to epsilon 2, dm is equal to epsilon m. So the two Markov chains are exactly the same, not asymptotically, not approximately, equals for every n, b, epsilon 1 up to epsilon m, and every m, just equal. So that's why the numbers came out the same. The two processes are the same. Now, I'm not going to try to tell you in the minutes remaining why that's true, because I have 2 more lectures. and the next lecture I give is going to go back to carries, and I'll begin right at the beginning by explaining why this is true. Why is this theorem true? And you can see it, nowadays there's an aha proof, but you might try to think before tomorrow, or if you're planning to come or watch it, well, why is that true? There's a very nice reason it's the same. So I'm going to talk a little bit about, I'm going to talk a lecture's worth. So next lecture, which is carries and determinantal point processes. And determinantal point processes are one of the hot items in probability, and the kinds of probability I live in. Random matrix theory. There are all kinds of natural phenomena which are modeled by probability distributions on curves. And so if you take a piece of paper and light it on fire and look at the way the bottom of it moves, or if you take a coffee cup, coffee cups, when you put them down, you're a little bit of a slob. They leave rings. Okay, if you subtract off the circle and look at the fluctuations, that's one of our guys. There are hundreds and hundreds of physical natural phenomena that are well modeled by determinantal point processes, and carries are one of them, and descents are another. And I'm going to try to tell you that as an introduction to that part of probability, but I'll start by trying to explain why this theorem is true. And the final lecture, lecture 3, is shuffling and geometry. And so I'm going to go back to shuffling and try to explain how there's a huge generalization of shuffling that is surprising if you haven't seen it before, and even if you've seen it before, which is called random walk on chambers of a hyperplane arrangement. And all of the nice math of shuffling goes through, and so there's very nice math coming. So now let me say another sentence or two before letting you ask if you want to ask something. Well, first of all, so if you're a certain kind of mathematician, the permutation group is a special group of a finite reflection group. It's a group of type A. And it's just natural to try to think, well, what does it say for type B? And type B is the hyperoctahedral group, the group of sign permutations. And when Dave Beyer are talking, we're in the Harvard math department. Well, it's have to be grown-up mathematicians, not just shuffle cards. So how does it go for type B? So what's a type B shuffle? Well, you cut off about half the cards and you turn them face up, and then you go like that. It's a kid's shuffle. How annoying, right? So you want to shuffle enough so that not only the arrangement, but the up-down pattern is random. And for all types, actually, for all, including E8, all of this math goes through in some reasonable fashion. And so that's a thing that's true. And with adding, Don Knuth's favorite number system is balanced ternary. People design computers and work with digits that are not just 0 up to 9, but sign digits. And so there's a notion of sign digits in this, and if you work out carries for sign digits, it's exactly dual to type B shuffles. And so that's a very nice story. Now, it's a nice story because the math is nice, but in fact, I did consulting. Nowadays, casino machines, casinos use machines, and I got hired by the largest manufacturer of casino shuffling machines, Shuffle Master it's called, to try to study their shuffling machines. And it was some complicated thing that the engineers had made. I tell the story over coffee or something, but it turned out that exactly the math that was needed to understand their shuffling machines was type B shuffle. So, okay, math strikes again, right? Right. So one thing I want to do for a sentence is to just tell you what is in the references. So the talk I gave today is a paper with Dave Beyer called Trailing the Dovetail Shuffle to Its Lair, and it's a readable paper. The wonderful paper by John Holt, it's just a wonderful paper because he not only proves the theorems, he tells you how he came to think of them, and he does the math experiments on the computer using Mathematica, I'm sorry to say, and but it's just a great paper. The paper that shows that these two are the same, if you want to look at the proof of this theorem and see many different variations, is a paper I wrote with Jason Fullman called Carry Shuffling in an Amazing Matrix. The connection, so for the next lecture, if you want to see what the math is going to look like, the connection between carries and the math of carries, determinantal point processes, and many applications thereof are in a paper I wrote with Alexei Borodin and Jason Fullman on adding a list of numbers and other one-dependent determinantal point processes. And finally, I thought when I made up this handout, I could say, see the AMS, but Jason and I wrote a book called The Mathematics of Shuffling Cards, and it'll be out in April. So, it's all done. It's being printed as we speak. And so just to say, this talk was called Adding Numbers and Shuffling Cards. I certainly told you some things about adding numbers. I certainly told you some things about shuffling cards, and I hope I gave you the indication that they're related. For the students in this room, I want to add one thing. You know, how do you think about learning math when you're a youngster, right? This huge areas, you know, logic, algebraic geometry, probability, you know, modern algebra, analysis of every flavor, how to go about making your way in this mathematical jungle that we're in. Well, I just gave you an example of something that's worked for me, which is instead of trying to learn all of mathematics, pick a problem you're interested in. It can be a pure math problem. It can be a really applied problem like adding numbers or shuffling cards, and follow that thread and just try to actually think about it. And I found that to be very successful way of learning math. That is, you have to be honest and really follow wherever it leads you. If it means you have to learn about crystalline cohomology, good, go learn about it. No, I mean, it does go that way, but there is math, there are everyday problems, you know, how people come to sit in a room, try to make math out of that, how the dust settles in the corners of a room. There's math all around us, and I just gave you an example of two of the simplest things, adding numbers and shuffling cards.
So, any questions?
And complaints are okay too. Yeah. Oh, get up and yell. I'll hear you.
I'm interested in the trick, the magic you teach me.
Uh-huh.
And But the problem is, if you have one deck of card, you can have only finite number of increasing sequence.
Yes.
Maybe 26, I think.
Right.
But
that's the mean. But the chance that it's 32 or few, the 32 or fewer is not. It's 0.75. But go ahead. Yes.
And then the problem is that.
But we're only shuffling 3 times.
Three
so
times.
You can have at most 8.
That's my problem. That.
What's your problem?
When does that break up? How many times?
You want to do the trick and have somebody shuffle it 10 times? They'll kill you.
Okay.
It's boring. Just imagine you tell somebody shuffle, shuffle, shuffle. When does it break up? It breaks up at 7. That's what our theorem says. That is it. At 7, you can't do the trick. And we discuss that very, very carefully in the paper with Bayer. That is, actually give the numbers. And if you're really thinking about but you know, if you're actually doing the trick, shuffling twice is, for most people, it's pretty good. If you want to do the trick, first practice it shuffling once. You know, take a card out and see if you can find it. And then shuffling twice, it's harder. And we say practically how to do it. It is important to give instructions that the card that they pick out has to go in the middle of the deck. If they're just some troublemaker, they might take the card out and put it back on top, and that won't change anything, right? So you have to say, put the card back in the middle of the deck, but that'll break, that'll make you a new rising sequence. But I'm sorry, but I don't. Your question is silly. That is, no. I mean, nobody would dream of doing a trick where you have to ask the spectator to shuffle more than 3 times, right? And if you want to do that, they're going to throw things at you. So I want to protect you.
Okay. Thank you.
There was a Professor Duncan.
Yeah, Duncan.
Well, my silly question is also about the card trick, and it is, what is the carries counterpart to the card trick?
I don't know. The question is, does the card trick translate into something about carries? I don't know, but let me say something that will allow us both to think about it before our next meeting. And so, as you could tell, carries are interesting, and they're really quite interesting. And at some stage, you get to thinking, well, what are carries as part of math? You know, carries, kids learn to carry, right? But what is it as math? Where does it come in math? And the answer is carries are cocycles. And so let me explain for those of you who didn't learn this part yet. If you have a group like the integers mod 100, okay, and if you have a subgroup like the integers mod 10, sitting in the integers mod 100 is 0, 10, 20, 30, up to 90, okay? That's a subgroup of the integers. And then you choose coset representatives. Well, the usual coset representatives would be 0 up to 9. And unfortunately, the sum of 2 coset representatives isn't always a coset representative. So when we do group cohomology, when we learn basic group theory, we understand that the product, the sum of 2 coset representatives, of course, it's some coset plus a factor set, and those factor sets are the carries. And so carries are cocycles, and it's exactly cocycles. And the next time I'm going to explain how a lot of the math that I did carries through to essentially an arbitrary group and a subgroup and a choice of coset representatives. So there's a lot of freedom in exploring the question, but I don't know the answer. But something to think about. If you think of carries as cocycles, maybe for some other group, or but I don't know. It's a reasonable question. I never thought of it, so I'll think about it.
Any other questions?
So in the X-Euler theorem, I try to understand your theorem. So you assume uniform distribution for the 18 number and the uniform distribution for the card shuffle.
Right.
What's the role of the uniform distribution in your theorem?
It's crucial. It's crucial. If I change the uniform distribution, in the whole carries thing, if I change the role of the uniform distribution, all the nice math goes away. But the way I think about it you know, we do that all the time. You know, we say, well, what do typical numbers look like? In typical numbers, we often say, let's choose a number at random. And so choosing the digits uniformly doesn't seem like such a bad assumption, but you could try to change that. And I did try to change it, and the math didn't come out nice. So I don't know what else to tell you, right? I was, I haven't found them, but no, why not? I mean, you know, because it's something nice is going on, and I don't know a neat version with other distributions. But I'm assuming uniform.
Okay, if there's no other questions, so I will, sorry, I neglected to say this is a 3-day event, and Professor Diaconis already told us that he's going to talk about he's going to talk about tomorrow and the day after. And so there will be some tea served before the talk. So let's thank Professor Diaconis again. Okay, see you tomorrow at the same time.
Hello. Oh, one down.
That's wonderful.